and Dimitrios Tsimpis is going to talk to us about the relative scale separation in sphere orbifolds. Welcome, Dimitrios.
Thank you very much. Thank you for the invitation. So I will be talking about this paper that appeared this morning and has some overlap with the recent paper by Collins, Jafferis, Bafa, Zhu, and Yao. So consider an Einstein gravity in P plus Q dimensions, say coupled to Q form or to a P form by Hodge duality. This theory admits the so-called von-Rubin solutions, which are of this type, ADS P times MQ, where MQ is some Einstein manifold of positive curvature. Now, it is amusing to note that in the limit of high dimensions, when the number of dimensions goes to infinity in this way, these solutions admit parametric scale separation. However, embedded in string theory, of course, we don't have the freedom to take the infinite dimension limit, and they exhibit what is called an absence of scale separation, in the sense that the radius of curvature of ADS is of the same order as the radius of curvature of MQ. So we can define some sort of order parameter for the scale separation in this way, where mkk squared is the lowest, the first eigenvalue of minus the scalar Laplacian on the internal space. And of course, this applies to direct products like this. And as we heard earlier, if we want to talk about warp products, we need to slightly modify this Laplacian. There are different definitions of the order parameter that we can adopt, but this would not be so important here, as I would be talking about what I call a relative scale separation. Now, other solutions are known, which are more complicated, have different profiles, etc., but they all have this feature that this order parameter is of order 1. And I'm talking here about so-called pure supergravity solution, namely, I'm not allowing any sources or things like that. So it can be argued that scale separation, in fact, requires the presence of orientifolds. And indeed, in the presence of orientifolds, there are the so-called DGKT vacua, which appear to, and related solutions that appear to enjoy a parametric scale separation. And the view from the 10-dimensional type 2A supergravity description, they belong to a well-known supersymmetric ADS4 SU3 structure compactifications class. And in particular, they require smeared O6 planes. Now, a lot of people have pointed out that smeared orientifolds don't make sense, but the hope is that maybe DGAT can be described as some sort of zeroth order approximation to a full-fledged solution. And indeed, recently, there has been some first order version of this, which is localized and is first order in some certain flux expansion, large flux expansion. And all the story of scale separation has received a renewed interest recently with the within the Swampland program, and in particular, the strong ADS conjecture would seem to rule out the DGKT. Now, starting from a space without scale separation, where the two radii of curvature are of the same order, One could try the following. One could try to orbifold the internal manifold by some finite group, gamma, say. And now the volume after orbifolding would be reduced by a factor of gamma to the 1 over q, where q is a dimension. So naively, you would think that, well, the radius of curvature should also go like this. And now say that your finite group is part of some infinite series, which is parameterized by n of finite groups, and whose order goes to infinity as n goes to infinity. So this would seem to offer a very simple way of achieving a parametric scale separation. Now, this naive expectation fails for two reasons. First, the orbifolding may act on just a subset of the directions. And this is very clearly seen in this example where I have drawn the orbifold of the two-sphere by the cyclic group Zn of order n, where the generator of this is rotation along the north-south axis by a 2 pi over n rotation. So as you can see, the longitudinal direction is reduced by a factor of n, but the latitudinal direction is intact after orbifolding. Secondly, if gamma has fixed points, then the orbifold will be singular, and its description within supergravity would not be globally well defined. Now, you can have singular orbifolds in string theory, but if the orbifold is not smooth, there are light modes which are localized at the singularities, and these don't decouple in any limit. Now, here I will be considering this case of sphere orbifolds, let's say the Q sphere with gamma, a subgroup of SO Q plus 1. And it's useful to think of gamma, the finite group, as being as acting on the angular coordinates of an ambient R Q plus 1. And now the orbifolding, as I said, does not change the local properties. So if you stay away from the singularities, you still have a solution, but you don't have a global description. And in addition, in general, the orbifolding will break all or part of the original supersymmetry. Now, in certain cases, you can have sphere orbifolds of this type, which can be thought of as the near horizon limits of brane setups in flat space, where you can employ perturbative string theory to describe them. And the two examples I have in mind are these two, where the first one is D3 branes localized along R1,3. And here we have D0 branes along the time direction and 4 stacks of D4 branes wrapping cycles in the Calabi out here. And in each case, you can orbifold the space transverse to the branes. Let's say RQ plus 1, so Q is 5 here and 2 here, by a finite subgroup of SO Q plus 1. Think of the transverse space as a cone over the Q sphere. Take the near horizon limit, and then you end up with these geometries as your near horizon limit. Now, the spectrum consists of twisted and untwisted sector states. The untwisted sector is simply the projection of the theory before orbifolding to its gamma invariant states, and in particular will contain the gamma invariant supergravity states as a subset, calcicline modes, etc. When the orbifold is smooth, all the twisted sector states have masses which scale as radius of the sphere mod alpha prime, because you can think of them as stretching between different points of the sphere, which are identified under the orbifold action. And in the supergravity regime, where we demand that the radius be much bigger than the string scale, these twisted sector states will be much heavier than the calcicline states. However, when the orbifold is singular, these twisted states will not decouple. Now, for smooth orbifolds in the supergravity regime, the order of scale separation is determined by the gamma invariant states in the spectrum of the scalar Laplacian on the sphere. For singular orbifolds, this calculation will just set the limit, the scale for the massive gravitons. Now we can define the order of relative scale separation as this ratio where mkk mod gamma squared is the first eigenvalue of the gamma invariant spectrum on the sphere. So that the total scale separation will be given by this. Now, a systematic calculation of this was not available in the literature, and it would be interesting to have, even if parametric scale separation is not expected, at least to know the exact value of R would be interesting in cases, for example, where one would like to construct an effective theory in ADS. So what I'll be talking about is the calculation of this order parameter, the relative scale separation, in these two cases, where gamma in the first case is a subgroup of SO3 and a subgroup of SU3 in the second case. Why SU3? Because this orbifold is known to be unstable when it's non-supersymmetric, and it is not supersymmetric unless gamma is a subgroup of SU3. So let's start with the S2 case as a warm-up. For gamma, a subgroup of SO3, this can be done by brute force, is simple enough. The idea is the following. We know that the eigenfunctions of the scalar Laplacian are the spherical harmonics, and spherical harmonics are in one-to-one correspondence with homogeneous harmonic polynomials in R3. Well, here's some basis for the first few degrees. And we are looking for the lowest degree invariant under gamma. Now, let's say that the lowest degree invariant occurs at degree k. Then this will be equal to this ratio here, where q is 2 in this case. And so the relative, we have to divide by the same expression, but for k equals 1, which gives just q over ls squared, and their ratio, which I defined as r, is given by this. Now, the classification for the finite groups of SO3 was known in the 19th century, and consists of two infinite series, the cyclic groups, dihedral groups, and the groups of rotational symmetries of the Platonic solids. tetrahedral, octahedral, and icosahedral group. And we need to know their generators, which I've listed here. We can check the basis of harmonic invariance to see if they are invariant under the generators, and it turns out that they're not for the first 5 levels. And the first invariant occurs at degree 6 and is given by this linear combination in our basis, which results in this relative scale separation. Now, this way of doing it becomes rather clumsy as we go on. So we would need something slightly more efficient to generalize this to the S5. And well, the methods that are adapted for this are from invariant theory. So let me say a few words about this. Starting from any polynomial, let's say vector x here just groups together all the variables. An invariant function can be constructed by applying to it the so-called Reynolds operator. So here, G is the finite group. Little g is an element in this group which acts on the variables in some representation R. The number of invariants of homogeneous invariants, not necessarily harmonic, is generated by the so-called Molian function, which is defined as here. And if you want to know the number of linearly independent invariants of homogeneous polynomials of degree m, what you have to do is expand this in Taylor expansion in lambda and look at the coefficient of order m. And there's also a way to obtain the number of algebraically independent invariants and their degrees, but that will not be so important here. Now, let's go back to the icosahedral example that I mentioned and see how we would do it in this way. Now, the group here, the finite group, is the icosahedral group. It acts on the 3 coordinates of R3 in the 3-dimensional representation. We can construct the Molian function since we know, well, we know the generators. We can write a simple code that generates all group elements and therefore calculate this. Expand it in Taylor expansion, and we see that there is, well, 1 invariant at degree 0, 1 at degree 2, 4, and 2 at degree 6, etc. The degree 2 and 4 invariants can be obtained explicitly by acting on x squared and x4 with the Reynolds operator, and what we get is this. The fact that they're invariant simply reflects that I is a subgroup of SO3, so this is just the norm of the vector. And we can see, after having constructed them explicitly, that they're not harmonic. At degree 6, we can apply the Reynolds operator on this and this monomial to construct the 2 linearly independent invariants, for example. Neither of these is harmonic either, but there is one linear combination that's harmonic, and this provides the second. This provides the 2 linearly independent invariants and the harmonic invariant that we constructed earlier. We see that is exactly what we found earlier with the more brute force method. And well, I mentioned that, by the way, they're not algebraically independent. Anyway, this is not so important here. Now let's move on to the 5-sphere. Now, a gamma is a subgroup of SU3. It acts on the complex coordinates of C3 in the three-dimensional complex representation. But now we're interested in invariant homogeneous polynomials of degree 6. So in those variables on which our group acts in the representation 3 plus 3 bar. We calculate the Molian function using this formula now, where G is an element of gamma. And we can also construct the Molian function that corresponds to the free representation, and that will count holomorphic invariants. And we're looking for those invariants that are in addition harmonic with respect to the Laplacian on R6. So we have to know the classification of subgroups of SU3, finite subgroups. And this has been, the first classification was given over a century ago with additions and minor corrections appearing through the years, and some of them quite recently, in fact. And we have this list here. So we have the abelian groups of this form, which are groups of diagonal matrices. We have finite groups of this form where A is a finite group of U2. We have 2 infinite series and 8 exceptional cases, usually denoted by sigma, and some notable sub-series, but I'm not going to bore you with all the details. Let's look at one example. So this is the 5-sphere modded out by this exceptional group of order 648, which is generated by, can be generated by these 2 matrices. Well, as I said, we can use the program to calculate all the elements of the group, and also the Molian function and its expansion and power series. And from that, we see that there is one invariant of which is the constant of the degree 0, 1 at degree 2, 1 at degree 4, 1 and 2 at degree 6. Now, at every even order, there is this invariant, which is never harmonic, well, except for n equals 0, and simply reflects the fact that our group is a subgroup of SU3, in fact, of U3 here. So this accounts for all the invariants here, except the second at degree 6. That second invariant can be obtained by applying the Reynolds operator on this monomial, and it looks like this. Now, neither this nor this are harmonic, but this linear combination turns out to be harmonic, and this means that we have our first harmonic occurring at degree k equals 6. Now we can also, and this we can repeat for all the subgroups in our list, and we can also see if they admit killing spinners. There's an easy way to see that, and whether or not they're smooth, because the classification of singular orbifolds is known. And so here's the upshot of this analysis. For orbifolds of the 2-sphere, we have the 5 different cases in our classification. The order of the finite group and the degree at which the first invariant occurs. And you'll see that in the cyclic group Zn, there is no scale separation at all, as also confirmed by our little image earlier of the S2 mod Zn. We have some scale separation for dihedral and higher scale separation for the exceptional cases, and the highest is for the icosahedral group. All these orbifolds are singular, and none of them admits killing spinors. Now, for the S5 orbifolds, here are the infinite series. This is the order of each finite group. And this is the order, the degree at which the first harmonic polynomial occurs. And this is the relative scale separation in each case. Now, these two, well, the Zn subcase here and this one are smooth, but the rest are not. And this result also is contained in the Boston paper I mentioned earlier. Now, of course, all of those are supersymmetric. They admit killing spinors since we started with subgroups of SU3. And these are the 8 exceptional cases. So we see that the highest degree of scale separation is attained again in the exceptional case, in the 3 cases listed here. And all the exceptional cases are singular. And all of them admit killing spinors. As I said, they are subgroups of SU3. So this brings me to the conclusions. I have shown you the calculation for the relative order of scale separation in these 2 cases for gamma subgroup of SO3 or gamma subgroup of SU3. And we confirm that there is no parametric scale separation, but nevertheless, it might be interesting to know exact value of R. And this might be also useful for applications that construct effective theories in anti-de Sitter. The highest scale separation occurs for the exceptional cases in both examples of the 2-sphere and the 5-sphere. In both examples, the first invariant harmonic polynomial is a degree 6. And in both cases, it is a singular orbifold for which we attain the highest scale separation. And so I hope I have convinced you that these methods are quite efficient for analyzing these cases and are easily generalizable to other orbifolds, and it would be nice to have a systematic study of the other cases. So thank you for your attention.
Okay, thanks, Dimitrios. So we have.
Should I go? Should I go to? Should I quit the shared screen or what?
I would say we wait in case there is a question that needs something from the presentation. Sure. So, are there some questions? Well, if there's still first no question, I'll ask you a question. So you think that for other orbifolds, I mean, you say the method you can't generalize. So do you expect like similar results, that there would be no parametric scale separation, that you have still this R of order 1?
Well, yes, I do not expect a parametric scale separation, but I don't think there is a, well, there is some results, but they are also case-by-case results for types of orbifolds that arise by probing, by arising by putting brains probing singularities in the paper that I mentioned, that go beyond sphere orbifolds. So they have singularities in where the transfer space is Calabi-Yau singularity of certain types, and there they also find bounds that are excluding parametric scale separation.
Okay.
But I think, well, I don't know if that would make any difference. It doesn't make any difference here, but in their case, they insist on smooth orbifolds. Well, they also have some results for singular orbifolds. No, I don't believe there is any theorem that says there is no parametric scale separation, but indeed, I would be surprised if there was.
If there is, okay. Great. So, okay, just giving time in case there is another question. Something else I didn't grasp completely. You were saying something about that when the order grows, I mean, then like the naive expectation would be that you can reach this parametric scale separation. So
Yes.
can you explain once more a little bit, I mean, why this naive expectation fails by growing?
Well, here what happens is that that's the easiest case to see it quite explicitly. What happens is that when you mod out by the finite group, indeed you shrink some of the directions, here the longitudinal direction, by a factor of n, which is indeed the order of the group here. So I've reduced the size of this direction by a factor of n, but have done nothing to reduce the latitudinal direction. And when you calculate the spectrum, you still get Kaluza-Klein modes that are exactly of the same order as before.
I see. So you leave some part, some direction.
Yeah, so just the fact that this longitudinal direction is intact gives you no scale separation at all. And that here, the invariant here is just a monomial, z, which is not touched by the rotation, which acts on the xy plane.
Okay, yeah, now it's clear for me. Thanks.
Welcome.
So, any other question or comment? So if not, we finished like at the exact time we were supposed to finish. So thanks, Dimitrios, again, for the very nice talk, very clear.